Yeah.
Hello everyone, good morning.
Morning.
So your exam is coming, right? And you know the date, right? October 2nd. So tomorrow we will have just a regular class, no exams, like no quizzes will be there. We'll basically try to review whatever we learned up to this point. We can try to solve some questions, mathematical questions and other stuff. But most importantly, I want you to raise more questions. What kind of problems you're facing, and we'll try to answer these questions. Okay? So bring up more questions as possible because this is the last week before we have the first exam. And today we will try to do some mathematical problem solutions that might be helpful for you for the exam. Okay? So, in our class we talked about how to calculate electric fields for different geometries. Right? So, what if we try to solve a problem that talks about electric field calculations for two different kinds of objects. So let us say that we have a long piece of wire, and we know that if this wire is very long, then at some point this guy is going to create some electric field, and if the wire is very long, we can consider it's infinite, and the electric field will be radially outward along the x-axis, provided that this guy is oriented along the wire. Now, the corresponding electric field at this point P can be expressed by K rho L divided by D, where rho L is your charge distributions over this entire wire, and D is the distance between the point and that long piece of wire. And we can also write a corresponding vector x hat in order to show that what is the direction of the electric field. So if I give you a problem like the following, let's say we have a three-dimensional space, x, y, z, and we have two long line of wire. Let us say that one of the wire is along the y direction, and the other wire is probably in the xz plane somewhere. It's lying in the xz plane like the following way. So it's a three-dimensional picture, so I'm not sure that if you guys you're getting the picture here. So let me explain one more time. One of the wire is straight along this y-axis, and the other guy is along this xz plane, which is xz plane is actually radial. It is out of the plane of this board, and we put a wire on this xz plane. Okay, the wire is in parallel with the z-axis. So if this is the situation, how can I calculate an electric field? Let us say at some point P. Let us say at this point P. And what would be the direction of the electric field for such a situation? So in order to find, do you guys understand what exactly is drawn here? So it's a three-dimensional axis. Let's say our board is XY plane, and the Z-axis is out of the plane. It's outward from the board. So one guy is exactly on the plane of the board, and the other guy is like the following, that it's a long piece of wire, it's out of the plane of the board, like the following. And we're trying to see that what is the electric field at a point P, which is in between those two wires. So how can I calculate an electric field at that point P? So we know electric field can be calculated if we use the principle of superposition. That means, instead of considering the entire system at the same time, we can consider the impact of electric field for only one particular guy. Let's say electric field is coming from only this long piece of wire along the y-axis. We'll calculate the electric field. And then we'll assume that this wire is not there, it's just vanished. We only calculate the contributions from this other guy, which is along this x-ray plane in parallel with the z-axis. We'll again calculate the electric field. And in both cases, we will consider what is the direction of electric field. So electric field would be a summation of two different components. Let's say E1 and E2. E1 might be coming from this guy, which is along the y-axis, and E2 might be coming from the other guy, which is along the x-ray plane. So let us calculate the first one. Electric field from this long piece of wire along the y-axis. And we are directly going to use this equation, 2k rho L by O. So 2k rho L by the distance d. Now we have to be a little bit careful here, because rho L for these two wires would be completely different. So maybe rho L for the first guy is probably one nanocoulomb per meter, and the rho L for this other guy might be 5 nanocoulomb per meter. And maybe the first wire goes to 0, 0, 0 point. The second wire, it might be going through, let us say, .0, 0 point. Let me write it in a better way. So the other guy passes through 10, 0, 0 point. The first guy passes through 0, 0, 0 point. That is our equation. And we want to calculate an electric field exactly in between those two wires. So in our case, the P point, which is of interest, it has a coordinate of 5, 0, 0. Okay? So if we try to calculate the component electric field E1, we know that the corresponding rho L would be 1 nanocoulomb per meter. So let us just put it like this. 1 nanocoulomb per meter. And the D would be the distance between the wire and the point of interest, which is 5. So let's say this is 5 meters. And I put the number 5 in the denominator. And for the second guy, the electric field from this wire would be calculated by taking into account that this has a charge density of 5 nanocoulomb per meter. So let us just put the 5 nanocoulomb per meter in the numerator, and then in the denominator, the distance between the point of interest and this wire is 5 meters. So let's again put 5 meters in the denominator. And then there is the tricky part. We cannot simply add them together. Remember that these are not algebraic summations, these are vector summations. So we need to take into account that what are their x, y, z component. Okay. Now we know that electric field for these wire, which is along the y direction, must be along the x-axis, right? So we can simply write that this side would be a x-directed electric field. How about the electric field from the other wire, which is along the xz plane? What would be the direction of the electric field for this guy? This way, right? Yeah. At the same axis, but in the opposite directions. So we should write this guy must have an electric field in the minus x hat direction. So in such a situation, the answer should be very simple. Like we can simply subtract one guy from the other one because they have exactly the same axis, just the orientation is different. Just the orientation is reverse of each other. So in that case, you can simply subtract one guy from the other guy. And value of A typically in air, in free space, is 4 pi epsilon naught. Where epsilon naught is a constant, and I give you the value of epsilon, 8.85 multiplied by 10 inverse 12 farad per meter. So if you plug in all these values, you'll get the final answer. Okay? So I believe the rest of the stuff you can figure it out by yourself. All right. So this was an easy situation. What if electric field has to be calculated not exactly on 500 point, but what if I want to calculate electric field at a different point? So let me redraw the situation one more time. We have our x, y, z coordinate, and we have a long piece of wire along the y-axis. We have another long piece of wire on this xz plane in parallel with z-axis, which goes to 10, 0, 0 point. The first wire goes along the origin, 0, 0, 0 point. And this time, maybe we want to calculate an electric field which is at a point, let us say, at 550. So previously we calculated electric field at a point which is 500. So exactly it was on the x-axis. Now we want to calculate electric field at a point 550. That means it has an x component and also it has a direction with a y-axis. Now this might be a little bit tricky situation compared to the previous one, because if we try to calculate electric field, we know that the first wire is going to create an electric field which is along the x direction, right? But how about the other guy? The wire which is along this x plane, what would be the direction of electric field from this guy to the point of interest? So the other component would be along this axis, right? So it is neither x nor y. That is, it has a component along the x-axis. It will also have a component along the y-axis. So this time, we need to divide all these components into their x and y-axis. And how we are going to calculate the case for such a situation. So let me erase this guy. And total electric field would be a summation of two different components, E1 and E2. Finding the value of E1 might be the easiest one. So E1 comes from the wire that is along the y-axis, and we know that the electric field would be 2K rho L divided by D. And this guy is going to be directed along the x-axis. So I'm simply going to put a x hat notation for this E1 component. And let me just put the value. Rho L is 1 nanocoulomb per meter. D is the distance, which is 5 meters from this wire to the point of interest with the x-hat component. Now E2, that might be a little bit tricky. So how we are going to calculate E2? We know that E2 must be directed along this axis, which I showed here with the arrow, right? So we have to divide this guy into two different components, but let's first try to write the total magnitude of E2 component. The total magnitude can be calculated as 2K rho L divided by D. Now let us see. Rho L is 5 nanocoulomb per meter. For this guy, it is rho L is 1 nanocoulomb per meter. What would be the distance between the point of interest, which is at 550, versus the wire, which is along this x-axis, which goes along 1000 point?
Square root of 50.
Pardon?
Square root of 50.
So how can I calculate it? Is there a way? Can we use some geometric formula?
I was saying the magnitude of the distance.
So all the values are here. Just help me to identify that how I'm going to calculate the magnitude of the distance. This distance. You know everything. You know this guy is 000 point. You know this guy is 1000. This guy is 550. So you can use Pythagoras formula in order to find out the distance. So this guy must have a distance of 5. This guy must also have a distance of 5, right? This is making sense?
The square root of 50.
So this guy, the hypotenuse, must be the square root summation of these two arms. That means the value of D must be the square root of the summation of two different distances, 5 square and 5 square. Right? Alright, so this is the total magnitude. However, we need to divide them into two components. One would be along the x-axis component, and the other would be along the y-axis component. So how am I going to do that? We have to find the corresponding angle that the direction of the electric field creates with the x-axis and also with the y-axis. So if I try to calculate the corresponding angle theta between the x-axis and the electric field directions. I can also calculate its corresponding component as cosine theta and sine theta for the coefficient of x hat and y hat. Is everyone up to this point? Is everyone following what's going on here? We're trying to find out the x-axis component and the y-axis component of the electric field so that we can algebraically add both of these E1 and E2. Okay? So now the challenge is how to find out the corresponding angle theta. Again, we are going to utilize some law of geometry, and we know that if this guy is theta, then this other guy must also have the same angle theta, simply because they are reverse of each other. So how can we find out the corresponding value of theta? We can use the formula of trigonometry, and we can say that cosine theta must be a ratio of base divided by hypotenuse. So your base is 5, and your hypotenuse is the square root summation of 5 square and 5 square. That's your cosine theta. In a similar way, if you try to find out sine theta, you can simply use this formula and find out the value of sine theta like this. Is everyone following? That's what I did here. So I just find out the value of cosine theta and sine theta by using trigonometric formula. Any question up to this point? That how we did it? All right. So once you plug in all these values here, then you can simply do the algebraic additions by taking care that we are going to add only x component with them, and we are going to add only the y component with themselves. So the x components here, we have two different x components. One is this guy, and the other is this guy. So let us just add them together.
Why would you find sine theta like that instead of just doing 5 over square root 5 squared plus 5 squared?
How do you find sine theta?
Why did you do it that way instead of just doing it?
Yeah, you can do it anyway, whichever way you like. Like sine theta is your height divided by the hypotenuse, right?
Yeah.
So you can find the height also.
Why wouldn't you choose to do it that way in the way, like, why would you use
No particular reason. No particular reason. You can simply ignore this law and use the other ways, whichever you find easy. So if we add all these x components, we are going to write this expression of electric field like the following way. We are adding the corresponding coefficient of x hat, and we are going to write the corresponding coefficient of y hat. and then you plug in all these values. Now we know all these things. Like we know what is the value of cosine theta, we know what is the value of sine theta, and we simply plug in all these numbers, and we'll get the final result. The final answer should have two different components. One is along the x-axis, and one is along the y-axis. Right? So in this case, we also need to take care of the fact that what is the direction of this x-axis. Like for this guy, which is along the y-axis, the electric field would be along the positive x-axis. For the other guy, the electric field would have a negative x-axis component and a positive y-axis component. You see? So when you add all these x hat component and y hat component, please also take care of the fact that what is the direction of the electric field. Is it along the positive x-axis or along the negative x-axis? So for the E1 component, x hat will have a positive component, right? For this guy, electric field will be along the positive x-axis. For this other guy, electric field will be having a negative x component and a positive y component. So make sure that your cosine theta must be multiplied by a negative factor. Okay? So in this case, please make special attention that this guy would not be positive, but a negative sign. Do you follow that why I change this sign? So please, people often make mistake. Pay special attention so that your sign is accurate. Okay? So this guy would have a negative sign. Alright, so we can ask questions like the following in the exam. Please pay special attention. Yes.
So for this problem and the previous one, we're assuming that L is much, much larger than D.
Yes. Very good.
Is that going to be like specified in the question, or we make that assumption ourselves?
So if the question says that it's a long piece of wire, then you may say that it's an infinite wire. But if the exam question says that the wire has a specific length, then you have to consider that this length might not be infinite. However, we spoke these things previously, and let me ask this question. So thank you, you brought this up. So let me write the question in the following way. Let us say our wire is not very long. I mean, it is finite wire. So if the length of the wire, of both the wire, is, let's say, 1 micrometer, and the distance of the point of interest that we are trying to calculate the electric field for is, let's say, 1 nanometer. So the distance of the point of interest is just 1 nanometer, and the length of the wire is 1 micrometer. Then would you think that you are going to use these equations, or you should use a different equation? What do you think? Electric field is going to be calculated for a wire which is not infinite, but it has a finite length of 1 micron, and we are trying to calculate an electric field which is 1 nanometer separated from this piece of wire. Can you consider this an infinite piece of wire? Yeah. Yes. This is an infinite piece of wire. Please do remember that scale matters. Okay? This is absolutely okay if you use the equations for infinite wire, and your answer should not be very, very far from the actual answer. However, if the distance is 1 millimeter, are you going to use these equations? Which equations you use? If the length is 1 micrometer for all of these wires, and we are trying to calculate an electric field at a distance 1 millimeter, what did you use? Point charge. Okay, so don't get fooled by the piece of wire. It's a point charge. Okay, you have to use the Coulomb's law, which says that the point charge create an electric field which is KQ divided by E square. That would be the equation. No matter whether I say it's a wire or not. Okay? It could be even a circle, a disk. It doesn't matter. As long as the distance is far away from the length, we can use the point charge approximations. Okay? So thank you for asking this question. This was very important for you.
So what if the length was like 1 centimeter and the distance was 1 millimeter?
Yeah.
Then
So then it's a little bit critical because you cannot directly use this equation. It's not actually a point charge. You can also use these equations because it's not an infinite piece of wire. So in those cases, we use formulas which are much more involved. For instance, in case of a finite piece of wire, let me write it down. Electric field for a finite wire should be twice K rho L divided by D and multiplied by a factor which is L over root over L square plus D square, where L is half of the length of the wire. Okay? So we might be using this formula. Alright? Okay. So this is one kind of problem that you might face in the exam. So please pay special attention to this kind of calculations. And the other kind of problems that we might see in the exam is probably calculating the divergence and the gradient. So the calculation of divergence basically helps us to identify wherever we have a source of charge in our point of interest of space. So let us say our electric field looks like the following. It has a mathematical expression which looks like the following. E equal to y and the corresponding vector direction is x hat. How do we draw this kind of electric field? So let us say we are trying to find out electric field on the plane of this board. And we are trying to draw the electric field. How we are going to draw it? Can you guys help? So let's first see what is the direction of electric field. It's in the x-axis, right? So if we try to draw some arrows, all these arrows will be along this x-axis. Right? So all these arrows will be along this x-axis. So this is one part. The other part is to take care of the magnitude of electric field. So it says the magnitude of x hat would be y. So this means if you go away from this y-axis, if you go further to the right, would you have a change in your y component? So let us say that we are trying to calculate electric field here versus we are trying to calculate electric field at some distance to its right here. At both of these points, the y component is same, exactly same, right? So this means if we try to draw arrows, these arrows will not change its magnitude if we keep going to the right or to the left. So all these arrows must be along the x-axis, and they must have exactly the same magnitude no matter how far we go to the right or to the left. So this is how it will look like. Now let us try to fill up the rest of the space with arrows. You say that it doesn't matter if we go to the right or left, electric field is going to be remaining same. What if we go, instead of right or left, what if we go up or down? So let's say if we go down close to the origin, would we see a change in electric field?
Yeah.
We should, because electric field depends on the y coordinate. So if you go down, your y coordinate is going to reduce, right? So your y component is going to reduce down, and at the point where we have the origin, we have exactly 0 electric field. So we are going to fill up this entire space with arrow one more time. But make sure that as you go down further to the close to the origin, your electric field component is going to reduce. This is how it will look. So what if I keep going down further? Let's say I go to the negative y-axis. What would happen? Would I have the electric field along the same direction? It moves in opposite directions, right? Does everyone follow that why it flips? Electric field always follows the corresponding sign of y. So if you are in the positive y, all your electric field will be along the positive x-axis direction. But if you go to the negative y, your sign will flip. So in that case, you're going to flip the direction of those arrows. So instead of having arrows in the positive x-axis, now we are going to have arrows in the negative x-axis. And what if you just keep going down, further down? What will be the size of those arrows? As you keep going down, the y is going to increase in the negative direction, right? So this means the size of the arrow would be going up, would increase as you keep going further down. So the arrows will increase in their magnitude. Right? All right. So from these diagrams, can you tell whether there is a source of charge somewhere in the plane of the board? Is it possible to have some charges? So you have to know whether there are some charges or not. Please remember that the charge is related to the divergence of electric field by Poisson's law. So the divergence of electric field is related to charge divided by the epsilon. And finding out the divergence of electric field should be following a differential mathematical equations. So divergence of electric field can be calculated by taking into account of the fact that the electric field has XYZ component, and we are going to differentiate all these XYZ component with the corresponding XYZ value, and then we will simply add them up. So from this diagram, does it look like that it has a source somewhere on the plane of the board? If you look at the distributions of arrows, does it occur to you that there is a source somewhere? If you place a box anywhere and make the box very small, you will see that whatever arrow is coming inside of the box is the same arrow that is going out of the box. So no matter where is the position of the box, the arrow coming in and the arrow going out is exactly the same. That means there is no net source or no net sink of charges in this plane of the board. Okay? Mathematically, if you calculate electric field, you can take the differentiation with respect to x. If you take the differentiation for this guy, what will be the result? So take only dx component, and the answer will be 0, right? So dy dx will be just 0. How about dy versus dy and dz versus dz? We have no x, y, and z component for these expressions, right? So this is why the other two terms will be 0. So eventually you will see that the divergence of electric field is 0 all over the places, and that's why it has no charges. Okay? If it has some charges on this plane, we must have some divergence on that particular point. Okay? So in questions, I may ask you to find out electric field and find out the corresponding divergence of electric field. Okay? So please also pay very special attention to this kind of problem. Does everyone follow up to this point? Let me change this electric field a little bit and try to redraw the new case. So let us say, instead of having an electric field of y x hat, what if our electric field is x hat? So in such a case, let us redraw the electric field. And this time, we know that it is dependent on x coordinate. So that means, if you go to the right or to the left of the y-axis, you must be having a different x component. That means your arrow, the size of those arrows, is going to increase or decrease. So, if you go to the right, your x component is going to increase. That means I'm going to draw arrow bigger and further bigger as we keep going to my right. If I go up and down, I'm going to change the y component, but my x component would remain fixed. So if I go up and down, I should not see any change of the size of the arrows. So if I keep going up, I should have exactly the same size of arrows, right? In a similar way, this guy has a bigger arrow. If I keep going up, the size won't change. Right? What if I go down? Again, the size doesn't change because the electric field is not dependent on the y coordinate. So it will look like a ball. Right? What if I come to the left side of y-axis? Would I have the same orientation of these arrows, or it will be different? It will flip, right? Because on the left side, the x will change its sign. So if I come to the left side, my arrow will flip their direction. Like the following. Does it look like that it has charges on the plane of the board? Does the arrow look like that there must be some net water flow coming in and net water flow going out? There should be, right? This is why the arrow is keep getting bigger as we go to the right or to the left. And if you use mathematical equations, try to calculate the divergence of electric field. By taking the differentiation of x, y, and z component of electric field. And you will see that this guy has a divergence of 1. There is no dy z component and there is no dez component. That's why we are going to just vanish them. The only x component will survive. And if you take the differentiation of ex with respect to x, we will get the value of 1. That means everywhere on this plane of board, we have a charge which is 1 unit magnitude. Okay, and this is why the arrows keep getting bigger as we go to the right or to the left. So we have charge actually everywhere, every point. We have charge here, we also have charge here, we also have charge here. And everywhere we have the uniform charge distributions. That is, it's a uniform sheet of charge. Okay? So this is another way of saying that you have a uniform distribution of charges over your entire plane, instead of just saying it out explicitly. So in question, in exam, I might ask you to solve some mathematical questions. The answer would be again just multiple choice. So you have to just figure out that which one is the right option. So in order to calculate these equations, you might need to solve this stuff in your loose paper. I'll try to bring some loose papers, but it's absolutely okay if you bring your own. Okay. And any question up to this point, that how exactly it's done, how the divergence is calculated, and from the field, from the divergence calculator, how we are going to calculate the corresponding charge density at a point P. All right. So if we all follow up to this point, let me just give you one more scenario, and maybe then we will conclude our class. So, let us say that we have a ring of charge with a density of rho L, and let us say we say that the rho L is 1 nanocoulomb per meter, and we are trying to find out the state of a proton at a distance d from that circle of charge. Can we find out how the proton is going to move if we have a circle of charge at some distance d? In order to solve this problem, let us first try to find out the electric field at this point P away from this circle of charge. So we know that if we have a circle of charge, then the corresponding electric field would be instead of D, let me write it H. H means the distance between the ring of charge and the distance of the proton. And B is the radius of the ring of charge. So in such a case, we can use this formula to find out the electric field at the position of the proton. So let us say our H is maybe 1 millimeter, and maybe the radius of the ring of charge is 2 millimeter. So we can find out the corresponding electric field by plugging in all these values. So K multiplied by rho, which is 1 coulomb, 1 nanocoulomb per meter, multiplied by H, which is 1 millimeter, multiplied by the radius, which is 2 millimeters. And in the denominator, we are going to put the value of H square plus V square, which is 1 millimeter and 2 millimeter. Take the summation, raise them to the power 3 by 2. You will get the final value of electric field. The electric field would be around the x-axis. If we have a negative charge on this ring of circle, then we are going to have a negative x-axis directed electric field. Right? So if we try to calculate the corresponding velocity or acceleration of the proton, how we are going to find it out? So acceleration of the proton can be calculated by using Newton's formula, which says that force is proportional to acceleration times the mass of proton. And to find out the value of force, we can simply calculate it from electric field. If we multiply electric field with the charge of proton, we will get the corresponding force. And in order to find out the mass, we simply look up Google and I just remember that it's roughly 10 inverse to 87 kilograms.
1.67.
1.67. Thank you. So for the mass, I'll be using the mass of proton, and to calculate the force, I'll be using the charge of proton, which is probably 1.6 into 10 inverse 19 coulomb multiplied by the electric field divided by their mass. So if you plug in all these values, you will get the corresponding acceleration of protons for a ring of charge. Okay? So you may see some questions like this in the exam as well. From the accelerations, can you find out what is the corresponding velocity? How do you do that?
Integrated.
Integrate. You integrate accelerations over what? Over the variable of time. So integration of acceleration over the variable of time would give you the corresponding velocity of the proton. How you are going to find out? So let me erase this guy. we are to calculate the velocity of proton, we can utilize the fact that velocity of proton is an integration of accelerations over the time. Now, accelerations, in this particular case, acceleration is going to be just a fixed number, right? If the proton is at a particular point. However, if the proton changes its position because of the force, the acceleration is going to be a function of time, right? So you calculate the accelerations, you plug in the value of accelerations here, which is probably going to be a function of time. So instead of just a constant number, it will be a function of time, and you integrate it, you will get the corresponding velocity of the proton. So most likely in the exam, you will not be asked to find out the corresponding velocity because it's a little bit difficult. You will have to use computers to solve these equations. But this might be helpful for your project. For exam, we might be limiting our questions up to this point, where you have to find out the corresponding acceleration of protons at a point p. Yes.
Two questions. For the acceleration formula at the bottom, we have force equals QE. Is that the charge of the ring charge or the charge of that proton?
Good question. So, thank you for asking this. So force means that how much force do you experience at the position of the proton, and in order to find out the force, we need to take the electric field. The electric field must be coming from this ring of charge. So when we calculate electric field, this rho must be taking care of the charge density of this ring of charge. However, when we calculate the force, remember that the force must be a multiplication of the charge of the proton itself multiplied by the electric field. Okay? So the charge of the proton would be plugged in the following equations. But for the previous guy, the charge density must be coming from the ring of charge. Does that answer the question? Yes.
Is rho in the formula different from rho L used for the ring of charge?
No, just say.
Oh, okay.
So this rho is actually charge density, which is distributed over the entire circle. Thank you for asking this. Alright, so I think we discussed a little bit today regarding what kind of problems we might need to solve in the exam. And tomorrow we'll discuss few more stuffs like this. And then our exam would be on Wednesday, right? So you know the location of the exam also, right? It's on the ground floor. So we'll have class tomorrow, and in the following day also. In the following week, we were supposed to have a class on Tuesday, Wednesday, Thursday, but since Wednesday is the exam, I think it's better if we suspend the class on the previous day. That means on Tuesday, we will not have any class, but I will be in my office, so please come forward and talk to me if you have any questions. All right. And you can always email me if you have a question. All right. Thank you guys for your attention. We'll see you tomorrow.